So last class we started our new unit. We started with polynomials, and I decided maybe it was a crazy idea to start talking about just numbers in general and numbers in different bases. And so I just wanted to kind of go over that again. And if you've never seen numbers written out this way, this might be kind of wild to you. So the way we started was we started with a geometric sequence like this, and I just asked you to write the next couple terms. And you might notice, okay, this is just a pattern that's multiplying by 10. And every time you multiply by 10, you just add another 0 on the end of it. So like this is right here 1, and then 10 to the first, and then this is 10 times 10, 10 to the second power. This one's 10 to the third, this one's 10 to the fourth, etc., etc. In fact, I could even call this first one 10 to the 0. See how that fits with the pattern of the powers. And then we looked at a different pattern, a different geometric pattern. 1, 2, 4. Then we had 8. Then we had 16. Then we had 32, etc., etc. And we could write that as 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. In fact, we could write the 1 as 2 to the 0. And we did a couple more patterns. I think we also did 1, 3, 9, so we're taking powers of 3 here. Just multiplying by 3, just a geometric pattern. And so we can call that 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. So my point is that each of these geometric patterns just goes up by powers, and that each of them starts with the number 1. So then I gave you just like a random number, just a number that I just made up, something like, oops, let's not move it there, let's keep it down here. Something like, if I looked at the number 500 and, let's go 523. What 523 really means in our normal system of writing numbers is 500 plus 20 plus 3. In other words, it means 5 in the hundreds place, 2 in the tens place, and 3 in the ones place. But then I told you that numbers don't have to be written out with a base of 10. Numbers don't have to be written out in decimal. Decimal right here means base of 10. Numbers could also be written out in binary here, where each of the digits doesn't mean a power of 10. It means a power of 2. So if I think of the number 523 as a binary number, I could put a little 2 down here to tell you that I'm thinking of it differently. That doesn't mean 5 times 100 anymore and 2 times 10 anymore. It still means 3 times 1 because my binary pattern starts with 1, just like my decimal pattern starts with 1. And so when I look at my binary number here, it's 3 times 1, but my next number is 2 times 2, and my first number is 5 times 4. The reason is, if you look at your pattern here, when I wrote it in decimal, I used 5 times 100, that's 10 squared, 2 times 10, that's 10 to the first, and then 3 times 1. I'm just doing that same pattern with binary. 2 squared means 4, 2 to the first means 2. If I took that same number and wrote it in base 3, ternary, then I'm going to go 5 times 9 plus 2 times 3 plus 3 times 1. So the same number can be written out with different bases. If I actually calculated what this all came out to be, the binary version, 5 times 4 is 20. 20 plus 2 times 2 is 4, so 24. 3 more gets you up to 27. So the number 523, written with a base of 2, is 27, written with a base of 10. Same sort of idea if I took and actually calculated this out for my base 3 number. 5 times 4 is 45. 2 times 3 is 6. 3 times 1 is 3. So 45 plus 6 plus 3, I think that gives me 54 as a base of 10. Okay? And so this is really what's going on with the number system, is that every time when we see a decimal number, like a normal normal number, we see that every you move a place value over, you get 10 times bigger or 10 times smaller. But there's nothing like divine or magical about the number 10. It just happens to be the number that we usually write our numbers, and it's the base that we use. We have 10 fingers, so we use that base. And so my point with this lesson was just like, we don't have to use the base of 10. We could have used the base of 2, we could have used the base of 3, we could have used the base of 17. In fact, some cultures used to count to 12. If you think about your knuckles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you can count to 12 on one hand. And so if you wrote this number out with a base of 12, 5, 2, 3 with a base of 12 means 5 times 144, because that's 12 squared, plus 2 times 12, plus 3 times 1. That's a pretty big number. My point was that when you think about polynomials, those are really just numbers, 5, 2, 3, written in a base of x. 5 times x squared, plus 2 times x, plus 3 times 1. So anything that we can do with our numbers, like adding and subtracting and multiplying and dividing numbers, we can do those in base 10, we can do that in base 2, we can do that in base 3, base 12. We can also do that with base x numbers. In other words, we're going to work on multiplying, dividing, adding, and subtracting polynomials. And if you understand how that works just with numbers, and if you understand how that works with different bases, you have a better chance of understanding how it works with polynomials. All right, let me know if you got any questions. Happy to help out.